Good afternoon, students. Welcome to Analytics Powered Virtual Interactive Classes. So, how are you all? Hope all of you are doing great. Very good. So, today we are going to have our revision session. Okay. So, our today's class will be based on a chapter which we have already discussed about. Okay. So, without any kind of delay, let's start our class today. So, see, there is this very beautiful house, and inside that house, there is this little boy who is getting something inside from his cupboard, right? See, he got one shirt, basically his school uniform or school shirt. But see, there are some wrinkles in the shirt, isn't it? So, generally, what we do? We simply iron that, isn't it? So, similar to this, he also took his shirt to his mother and she is ironing that shirt. Now, he is having some kind of curiosity, okay? So, one question it's arising in his mind that how the heat is generated in an electric iron. Generally, whenever we use electric irons, the electric iron, it gets heated, right? So how does it get heated, isn't it? So this kind of question is coming in his mind. And after that, see, there is the science exhibition which is happening in his school. And there are so many booths where every student, they are presenting a science model. When they went near a science model, they saw a beautiful model. And this model was based on what? At the exhibition, there was a model of an iron nail wrapped with a wire connected to a battery. So basically, this model was made up of an iron nail which was wrapped with a wire connected to a battery. Now see, there is one switch which when we turn on the switch, what happens? The current starts flowing. And what happens? When the circuit was closed, the nail picked up iron paper clips like a magnet. See again, when she turned on the switch, what happened? The paper clips, iron paper clips were attracted towards the iron nail, isn't it? So this is what it's written here, that when the circuit was closed, the nail picked up iron paper clips like a magnet. When the current was flowing through the wires, what happened? The iron paper clips got attracted by the nail, isn't it? And when she turned off the switch, what happened? The electric flow, it stopped, and all the iron paper clips, they got detached from the iron nail, isn't it? So when the circuit was opened, the clips fell off. See, two things happened. When we turned on the switch, what happened? The paper clips got attracted. And when we turned off the switch, what happened? The iron paper clips, they fell off. So now they are thinking that there is no magnet present here, isn't it? But still, the iron nail is acting like a magnet, isn't it? So, iron paper clips are made of a magnetic material and can be attracted only by a magnet. But there was no magnet, only an electric circuit. Here, she didn't use any kind of magnet, but still the iron paper clips, they were getting attracted by the iron nail, isn't it? See, now they are also doing the same experiment. The girl, she turned on the switch, and as soon as she turned on the switch, all the paper clips got attracted towards the iron nail, isn't it? So now question comes that why are iron paper clips attracted to a current carrying wire? Why it got attracted? And as soon as she turns off the switch, what happens? Why are iron paper clips fall off when the current is switched off? So, whenever she turned off the switch, what happened? The iron paper clips, they fell off from the iron nail. So, why all these things are happening? Isn't it? So, today we are going to know about all these things. So, our today's topic is what? Electricity, magnetic and heating effects. So, today we are going to know or learn about this chapter. Okay, actually we already have studied about this. We are just going to revise that. Okay, see. So, now what are we going to learn? That does an electric current have a magnetic effect? Whenever the current is flowing, is there any kind of thing which generates a magnetic effect? To know that, we have to do one activity, and for that activity we have to collect certain objects. So let's see what those objects are. Collect a magnetic compass, an electric cell, a cell holder, two drawing pins, a safety pin, two nails, two pieces of connecting wire, one longer and one shorter, and two small pieces of cardboard. So all these things, these are the things what we have to collect for our activity today. Okay, so what are these things? One magnetic compass, an electric cell also known as battery, then a cell holder where we are gonna put the battery. Okay, two drawing pins, a safety pin, two nails, two pieces of connecting wire. One have to be longer in size and the other one will be shorter in size, and two small pieces of cardboard. Clear? Now, see, this is the battery or cell. We will put the electric cell or the battery inside the cell holder. So, connect the wires to the cell holder and place the cell in the holder. After that, what we have to do? After putting the cell inside the cell holder, we will connect the two wires which we took earlier. One was longer in size and another one was shorter in size. We have to connect both the wires with the two sides of the battery holder. See, this side we connected the longer wire and in this side we connected the shorter wire. Okay. Now we will be preparing one switch. So for that, what we have to do? We have to take one cardboard and we have to take the two drawing pins which we have already collected. Okay. So using two drawing pins, a safety pin and a piece of cardboard, make a switch. How to prepare it? Take one cardboard, take one drawing pin and insert the safety pin into the drawing pin and insert it into the cardboard, and take another drawing pin and in some distance, a little bit distant from the first drawing pin, we also insert that into the cardboard like this. Okay, so by this we can prepare a switch. Now after preparing the switch, we will make one circuit. So how to make it? Fix the middle portion of the longer wire stretched between the nails so that it is slightly above the surface of the cardboard, and finally attach it to one end of the switch. Now what we'll have to do? The part or the side which were connected with the longer wire we have to wrap it around the two nails which is inserted into the second cardboard like this. Okay, we have to stretch the wire a bit so that the wires are not touching the cardboard. And after that, what we have to do? Connect the second wire to the other end of the switch, and this shorter side of the wire we also connect this side to the nail drawing pin, and both the sides are connected with the drawing pins. One side, the shorter side to this pin and the longer side to another pin. Okay. Now, after that, what we have to do? Our circuit is ready. Okay. So, the thing is, after that, we have to do another small work. What is it? That place the magnetic compass beneath the wire between the two nails. So, in this position, we have to put our compass. Okay. Now, while observing the compass needle, move the switch to the on position to allow electric current to flow through the wire. See, now focus on the magnetic needle. What's its position? One side it's facing the north side and another side it's facing the south side, isn't it? Now, if we turn the switch on in on position, if we turn the switch into on position, what will happen? We simply just have to put the pin and attach it to the second drawing pin. Okay. See, when we attach the pin, what happened? The magnetic needle, it got distracted from its original position, isn't it? So, what do you observe? It got distracted from its original position, isn't it? So now, again, while observing the compass needle, move the switch to the off position. Off position means like this. We are detaching the safety pin from the second drawing pin. So what can we observe? What do you observe this time? That the iron compass needle went to its original position, back to facing north side and south side, isn't it? So, when we turn on the switch, the iron needle gets distracted. Okay. Why this is happening? Because when the current flows, the compass needle gets deflected from its original direction. Okay. Whenever the current is flowing, as we turn on the switch, that means what? That means the current is now able to flow through the electric wires, isn't it? So, due to this reason, okay, as the current is flowing, for that reason, the compass needle gets deflected from its original position. And whenever we are turning off the switch, when the current stops, the needle returns to its original direction. Okay. Now see why this is happening. Why this thing is happening? See, whenever we are bringing one magnetic bar near to one compass, what we can see? That the needle of the compass, it is getting deflected from its original position, whether it is north side or south side. No matter what side we are bringing closer to the electric compass, its needle gets deflected from its original position. Because why? The compass needle is a tiny magnet that deflects when another magnet is brought near it. Why this thing is happening? Because the compass needle we are talking about, which gets deflected from its original position, it's actually what? It's actually nothing else but a tiny magnet. Okay. And it gets deflected. Why? Because we are bringing magnet. It gets deflected whenever we are bringing a magnet near it. Okay, so the compass needle is a tiny magnet that deflects when another magnet is brought near it. Clear, everyone? See, whenever, but here in this case, we are not bringing any kind of magnet near the magnetic compass, isn't it? Then why does the compass needle deflects when current flows through the wire? Can any one of you tell me that why? Here what is happening? Here we are not bringing any kind of magnet near the magnetic compass, isn't it? But still, whenever we are turning on the switch, what is happening? The compass needle is getting deflected from its original position. So why is this happening? We didn't bring any kind of magnet near this time, right? But still it's getting deflected. Why is this happening? Let's try to discover. Okay, see, the deflection indicates that the current carrying wire has a magnetic effect on the compass needle. Okay, so from this we can assume that the deflection, it is occurring or because as the current is flowing through the electric wires, what is happening? One kind of magnetic effect is generating through the what? Through the electric wire. As the current is flowing, there is one magnetic effect which is generating. Okay, so that's why what is happening? The electric needle, the magnetic needle of the magnetic compass, it is getting deflected from its original position. Clear, everyone? And whenever we are turning off the switch, what happens? Then the current stops, isn't it? So when the current stops, the magnetic effect disappears and the compass needle returns to its original direction. So whenever we are turning off the switch, what is happening? The current also stops flowing. So as soon as the current stops flowing, the magnetic effect, it also disappears as it is connected with flow of the current. Whenever the current is flowing, only that time we can see the magnetic effect. Okay, we can observe the magnetic effect. But when the current is not flowing, at that time the magnetic effect also disappears. So that the compass needle do what? Compass needle goes to its original position or original direction. I hope everyone got it. Okay. So the region around a magnet or a current carrying where its magnetic effect can be felt, such as by the deflection of a compass needle, is said to have a magnetic field. Okay, so what is magnetic field? A region around a magnet or a current carrying wire where these magnetic effects can be felt, such as by the deflection of a compass needle, is said to have a magnetic field. Okay. See, here the current is flowing, isn't it? So when electric current flows through a conductor like a wire, it produces a magnetic field around it. And this phenomenon is known as the magnetic effect of electric current. So whenever we are turning off the switch, what happens? The magnetic field disappears when the current stops flowing. Okay, so note down, everyone. When electric current flows through a conductor like a wire, it produces a magnetic field around it. This phenomenon is known as the magnetic effect of electric current. Okay, so write down. Okay, everyone. Okay, when electric current flows through the conductor like a wire, it produces a magnetic field around it. Okay, so whenever we are allowing the current to flow or pass through the electric wire, there is this one magnetic field which is generated around the electric wire. Okay, so this phenomena, like by which we are able to produce magnetic field, is known as the magnetic effect of electric current. Because the current is flowing, only for that reason the magnetic effect is happening, isn't it? Whenever we are turning off the electric current, we can't find any kind of magnetic effect in that case. Only magnetic effect is only present whenever there is a flow of current. Okay, so this is why it is known as the magnetic effect of electric current. Clear? Now comes our first question of the day. Let's see what the question is. That compass needle is actually a tiny dash. So 4 options are there. Option A, piece of copper. Option B, aluminium rod. Option C, magnet. Or option D, plastic stick? So I am giving you the timer. Try to answer everyone. Okay. So what's the question is that a compass needle is actually a tiny dash. Four options. Option A, piece of copper. Option B, aluminium rod. Option C, magnet. Or option D, plastic stick. Which one will be the right answer? Tell me. Answer everyone, okay? What will be the correct answer? A compass needle is actually a tiny what? Is it a piece of copper or a aluminium rod or magnet or plastic stick? Which one is it? I can see so many of you already got the right answer. Very good. Remaining of you also try to answer, okay? And your time is almost up. And with that, your time is up. Let's see how many of you have got the right answer. Very good. So many of you have given the right answer. So our right answer will be what? A compass needle is actually a tiny magnet. It acts like a magnet, isn't it? So our correct option will be option C, magnet. A compass needle is actually a tiny magnet. Clear? Now see, there is this scientist. In 1820, the scientist Hans Christian Ørsted, a professor in Denmark, discovered that electricity and magnetism are connected. He was the first one to observe that electricity and magnetism, they are connected. How he discovered it? While giving a demonstration, he observed that the needle of a nearby magnetic compass deflected whenever an electric circuit was closed or opened. Okay, see what happened? One day he were giving some kind of demonstration regarding his observations. So while giving his demonstrations, he observed that whenever there is a current flowing through the wires, there is this deflection in the magnetic needle of the compass. Okay, whenever the current is flowing, the compass needle deflected from its original position, and whenever he turned off the current flow, the magnetic needle it went into its original position. So he was the first one to observe it. Okay, the things we have already observed through our activities, he was the first one to give those ideas in our mind. Okay, he was the first one to discover this. So while giving a demonstration, he observed that the needle of a nearby magnetic compass deflected whenever an electric circuit was closed or opened. After further investigation, so from getting this kind of idea, he started to investigate regarding this. Okay, so after further investigation, he concluded that an electric current produces a magnetic field around it. This discovery laid the foundation for the study of the relationship between electricity and magnetism. So from his observations or discovery, we were able to know the relationship between electricity and magnetism. So he was the first one to give us the idea regarding this. See, whenever there is a current flowing through the wire and around it there is one magnetic effect which is created. So he was the first one who, Hans Christian Ørsted. What was his name? Hans Christian Ørsted. He was the first one to tell us about the relationship between electricity and magnetism. Also, we can simply, if we want to call it, that whenever the current is flowing, there is this one magnetic field which is generating surrounding the electric wire, and due to that magnetic effect is generating. Okay, and for that reason the magnetic compass, the needle of the magnetic compass, it was deflecting from its original position. Clear? So his name was Hans Christian Ørsted. So our next question is also related to that. Okay. So, which scientist first discovered the magnetic effect of electric current? Four options are there. Option A, Isaac Newton. Option B, Albert Einstein. Option C, Hans Christian Ørsted. Or option D, Michael Faraday. Which one will be the right answer? Tell me. So, which among the following scientists first discovered the magnetic effect of electric current? Is it option A, Isaac Newton, option B, Albert Einstein, option B, Hans Christian Ørsted, or option D, Michael Faraday? Which one will be the right answer? Try to answer, everyone, okay? Is it Isaac Newton, Albert Einstein, Hans Christian Ørsted, Michael Faraday? Who was the first one to discover or give us the idea about the magnetic effect of electric current? So whenever there is electrical flow through a electrical wire, there is this magnetic effect which is generated around the electric wire. So who gave this idea for the first time? Is it option A, Isaac Newton, option B, Albert Einstein, option C, Hans Christian Ørsted, or option D, Michael Faraday? Okay, I have got so many answers already. And with that, your time is up. Let's see. Okay, very good. So many of you have given the right answer. We have just studied about it, isn't it? So, the answer will be what? Option C, Hans Christian Ørsted. So, he was the first one to discover about the magnetic effect of electric current. He was the one to discover the relationship between current and electricity, electrical flow and magnetism, isn't it? And next question is, let's see what's the next question is, a current carrying wire behaves like. How does it behave? There are four options. Option A, a battery, a magnet, option C, a bulb, or option D, a switch. How does it work or how does it behave? A current carrying wire. Your time already started, okay? Try to answer. A current carrying wire behaves like. Is it option A, a battery, option B, a magnet, option C, a bulb, or option D, a switch? Which one will be the right answer? A current carrying wire behaves like. Four options. Is it a battery or a magnet, a bulb, or a switch? How a current carrying wire behaves like? Try to answer, everyone, okay? Yes, already I have got so many right answers. Very good. Rest of the students also try to answer, okay? Very good, very good. So many of you have already given the right answer. And with that, your time is up. Let's see. Very good. So many of you have given the right answer. So our right answer will be what? Yeah, our right answer will be option B, a magnet. A current carrying wire behaves like a magnet, as whenever the current is flowing through the electrical wire, one magnetic field is creating or generating surround it, isn't it? So after generating the magnetic effect, what will happen? They will behave like a magnet, isn't it? In the first case, we saw one science model. There also, whenever the switch was turned on, what happened? The current started to flow and the iron nail, it also started to act like a magnet, and all the iron paper clips got attracted towards it, isn't it? So from this we can say that the current carrying wire, whenever the current is flowing through the wires, it behaves like a magnet. Clear, everyone? Very good. Okay, now next topic is, can we use electric current to make a magnet? Like by using this method, can we also produce one magnet? Let's see. For this we have to do another activity, and to do that activity we have to collect certain objects. So The materials which are required are, first we have to take one flexible insulated wire which is almost 50 centimeter, and after that we have to take one iron nail, another one electrical cell also known as battery, and tape. So after collecting these things, and iron paper clips also, okay. So after collecting these things, what we have to do? Tightly wrap the wire around the nail in the form of a coil and secure it with adhesive tape. Like this we have to wrap the wire around the around the iron nail. And after that we have to do what? We have to connect the two sides of the wire into the battery. Connect the ends of the wire to the cell like this. And after that we have to tape them from the both sides so that they don't move around, okay. And then what we have to do? Bring the nail close to the iron paper clips and lift it up. Do the clips hang from the ends of the nails? Now we have to bring the system or model which we have prepared near the iron paper clips, and after that we will have to observe that whether the iron paper clips are getting attracted towards the nails or not. See, the iron paper clips, they are getting attracted towards the iron nail, isn't it? So from this we can say that the iron nail, it's behaving like a magnet. But whenever we disconnect, what will happen? Disconnect the wire from the cell to stop the flow of electric current in the wire. Do the clips fall down? Like from one side we have to disconnect the circuit, and see what happened. All the paper clips that got attracted towards the nail, now they fell off, all of them. So from this we can say, when electric current flows through the coil, the clips cling to the nails. But when the current is stopped, the clips no longer cling to it, isn't it? In the first case, both the sides of the wire were connected with the battery, so the current was flowing, and at that time the iron paper clips, they were getting attracted towards the nails. But whenever we disconnect one side of the wire from the battery, what happens? Then the flow of current, it also stops, and due to that all the paper clips, they are not able to cling with the iron nails, okay. So here comes our next question. Let's see what the question is. When electric current is switched off in a wire, what will happen to the compass needle placed below it? Okay, 4 options are there. Option A, keep spinning. Option B, stay deflected. Option C, return to its original north-south position. Or is it option D, point towards the wire? So what happened? What the question is actually? Whenever the electric current is switched off, that means no current is passing through the electric wire, and at that time if we put one compass needle or a magnetic compass, then what kind of changes we are able to see in the compass needle which is placed below the wire? 4 options are there. Option A, will it keep spinning? That means the compass needle, will it keep spinning? Or option B, stay deflected. Option C, return to its original north-south position. Or option D, point towards the wire. So I have started the timer. Try to answer everyone, okay. What will happen? As try to remember the one which we have saw in our activity today. We prepared one circuit, isn't it? And there were 2 nails, and under the nails we placed one electrical magnetic compass, and whenever there was electrical flow, the compass needle deflected. But when we turned off the switch and the current flow also stopped, at that time what happened to the iron needle? magnetic needle? Was it spinning? Was it deflected? Or did it return to its original north-south position? Or it pointed towards the where? What will happen? Very good. So many of you already gotten the right answer. And with that, your time is up. Let's see. Very good. Very good. So, our right answer will be what? Option C. See, the deflection of the compass needle is observed only when the current is passing through the wire. But whenever we switch off the wire, that means what? The current is no longer able to pass through the wire. So from this, the deflected iron needle did what? It returned to its original position, which was facing north-south, isn't it? One side of the needle was facing the north side and the another side was facing the south side. So it returns to its original position. Clear everyone? Then next question, another question is there, that if you use a plastic paper clip instead of an iron paper clip, what will happen when it is brought near an iron nail wrapped in a wire carrying electric current? Think about it, okay? If you use a plastic paper clip instead of an iron paper clip, what will happen when it is brought near an iron nail wrapped in a wire carrying electric current? Okay, so this time we are using plastic paper clips. 4 options are there. Option A, the plastic paper clip will be attracted to the iron nail. Option B, the plastic paper clip will not be attracted to the iron nail because plastic is non-magnetic. Option C, the plastic paper clip will be pushed away by the iron nail. Or option D, the iron nail will stop being magnetic. So, I have started the timer. Try to answer everyone, okay? So, what will happen? Will the plastic paper clips will they be attracted towards the iron nail, or the plastic paper clips they will not be attracted to the iron nail because plastic is non-magnetic? Or option C, the plastic paper clip will be pushed away by the iron nail, or option D, the iron nail will stop being magnet. Which one will be the right answer? We are using plastic paper nails instead of iron paper nails. This time we are using plastic paper clips. Okay. So what will happen? Try to answer everyone. Okay. Yes, very good. I have got already so many right answers. And your time is almost up. And your time is up. Let's see. Very good, very good. So many of you have given the right answer. So our right answer will be option B. They won't be able to get attracted towards the iron nail because what? The magnet can't attract plastics, isn't it? Because plastic is non-magnetic substance. So if we are preparing the paper clips by plastic, that means what? They won't be able to attract it. Okay, the iron nail won't be able to attract it. So our correct answer will be option B. The plastic paper clip will not be attracted to the iron nail because plastic is non-magnetic. Clear everyone? Okay. Next question. Next question, and this will be our last question. Okay. So what is this? That which of the following materials, if used to make a wire, will not show a magnetic effect when current passes through it? 4 options are there. Option A, copper. Option B, silver. Option C, aluminium. Or option D, all of the above will show a magnetic effect. Which one will be the right answer? Try to answer everyone, okay? Which of the following materials, if used to make a wire, will not show a magnetic effect when current passes through it? Is it option A, copper, option B, silver, option C, aluminium, or option D, all of the above will show a magnetic effect? Which one will be the right answer? And with that, your time is up. Let's see. Very good. So many of you have given the right answer. Okay. So our correct answer will be option D. All of the above will show a magnetic effect. Okay. So with that, our class ends here. Hope all of you have understood whatever we have studied today. So we will be meeting in our next class. Till then, stay happy, stay healthy. Bye bye.